Dear students, welcome to the 18th online class of Control System Engineering. In last class we started steady-state error. In this chapter we studied about steady-state error and its specifications. Various test input used for steady-state error, and we studied about evaluation of steady-state error. We can have a zero steady-state error, a finite steady-state error, or a infinite steady-state error. Then we studied steady-state error for a feedback or a closed loop systems. In case of closed loop system, we can find steady-state error either by using equivalent closed loop transfer function T of S or we can also find this with the help of forward path transfer function G of S. Steady-state error with the help of forward path transfer function help us in better analysis and design of a closed loop system as per given specifications. Then we studied steady-state error for various test signals, and various test inputs used were step input, ramp input, and parabolic input. And then we find under what condition steady-state error would be zero, finite, or infinite for these input signals. Then we studied static error constants and system type. Now we will start. Dear students, after today's lecture, you will be able to specify a system steady-state error performance, how to design the gain of a closed loop system to meet steady-state error specification, how to find steady-state error for disturbance signal, and how to find steady-state error for a non-unit feedback systems. Dear students, content of today's lecture are steady-state error specifications, gain design to meet steady-state error specification, steady-state error for disturbances, and steady-state error for a non-unit feedback system. In this you will study how to convert a non-unit feedback system into a unit feedback system. Dear students, as studied in last lecture, static error constants can be used to specify the steady-state error characteristic of a control system. Just like damping ratio, settling time, peak time, percent overshoot were used as specification of a control system's transient response. In case of steady-state error, the position constant, the velocity constant, and the acceleration constant can be used as a specification for a control system steady-state error. Soon we will see that a wealth of information is contained within the specification of a static error constant. Dear students, let us explore what information we can extract from a static error constant. For example, if a control system has a specification of a velocity constant equals 1000, we can draw several conclusions from this. Like, if steady-state error exists for a stable systems only, then static error constants also exist for stable systems. So if velocity constant is given and its value is 1000, which means that our control system is a stable system. Here we have a finite value of velocity constant which means that its forward path have
one integrator.
so we conclude that forward path system is a type 1 system because only type 1 system have a finite constants. As kV equals 0 for type 0 system and kV equals infinity for type 2 systems. Next, a ramp input is a test signal because velocity constant is specified as a finite constant and the steady state error for ramp input is inversely proportional to kV. So in this case our test input is a ramp input. For step input the steady state error is 0 and for a parabolic input it will be infinite. The steady state error between the input ramp and output ramp is 1 over kV per unit of input slope. And in this case its error can be easily found by taking reciprocal of a velocity constant, which means that steady state error will be 1 over kV. Now students, this was the information we can extract from the given velocity constant. Dear students, in last slide we studied what information we can extract from static error constants. In next example, we have a control system whose static error position constant is given with a value of 1000. Now conclusion we can draw is that if static error constant is given, which means that our control system is a stable system. Position constant has a finite non-zero value, which means that it is a type 0 system. Type 0 system have no integrator in the forward path. And for this system, velocity constant and acceleration constant will be 0, as position constant is infinity for type 1 and type 2 systems. In this case, a step input is our test signal, as position constant is specified as a finite constant. For ramp and parabolic input, steady state error will be infinite. In this case, steady state error will be equal to 1 divided by 1 plus position constant, and this will be equal to 1 divided by 1001. Dear students, now we will study how to design a gain for a control system to meet steady state error specification. Students, we know that in a transfer function, positions of zeros and poles is fixed, where we can change the gain of a control system. With this gain, we can achieve the desired steady state error specification. In the upcoming example, we will study how to design a gain of a control system to meet the steady state error specification. Students, in this example, we have a closed loop system and we have to find the value of gain k for 10% steady state error. Means that difference between input and output will be 0.1 or 10%. Students, if you look at forward path transfer function, it is type 1 system because it have one integrator in the forward path, and the error related in the problem will be for ramp input, because for ramp input we will have a finite steady state error for type 1 system. So its error relation will be steady state error equals 1 over velocity constant, and this must be equal to 0.1, and we know that velocity constant is equal to limit s approaches to 0 s into g of s, where g of s is the forward path transfer function. Substituting the value of velocity constant equals 10 and solving for gain k, we have gain k equals 672. So for this gain of 672, our closed loop system will yield a steady state error of 0.11. After finding the gain, you must apply Rath-Hurwitz criteria to see for this gain our closed loop system is stable. Dear students, now we will study steady state error for disturbances. When we have a closed loop system and an external signal injected to the system and affect the performance is known as a disturbance signal. The feedback or a closed loop system are used to compensate the disturbance signal or unwanted signals entering a system. The advantage of using feedback or closed loop is that regardless of these disturbances, the system can be designed to follow the input with a small or zero error. Now we will study how these systems show compensation toward disturbances. In the figure, we have feedback control system where D of S is external disturbance signal injected between the plant and controller. Now we will find output of the system. For output, we will use superposition principle. At first, we will find output due to reference signal, which will be C1 of S, and in this case output will be equal to error E of S product with G1 of S and G2 of S. And in second case we will consider reference equals 0 and D of S as an input to the system. In this case, output will be equal to G2 of S multiplied by D of S. Now total output will be sum of C1 of S plus C2 of S, and total output C of S will be obtained. Dear students, we know that steady state error is the difference between input and output, or output will be equal to input minus error. Now substituting and solving, we obtain a relation for steady state error due to reference input and disturbance. Now 1 divided by 1 plus G1 of S product with G2 of S will act as a transfer function between error and reference input, where G2 divided by 1 plus G1 of S into G2 of S will act as a transfer function between error and disturbance signal D of S. Now to find steady state error, we must apply final value theorem. And for this final value theorem, we must assume that poles of characteristic equation 1 plus G1 of S into G2 of S must lie in left half plane, which means that our system is a stable system. After assuming a stable system, we obtain the relation for steady state error as E infinity equal ER of infinity plus ED of infinity. And this will be equal to limit S approaches to 0 as R of S divided by 1 plus G1 of S into G2 of S minus limit S approaches to 0 as G2 of S divided by 1 plus G1 of S into G2 of S multiplied by d of s. And relation for both er of infinity and ed of infinity are given here. Dear students, as studied that steady state error is equal to er of infinity plus ed of infinity. Here er of infinity is the steady state error due to reference input r of s, where ed of infinity is the steady state error due to disturbance signal d of s. Students, now we will find conditions for ed of infinity that must exist to reduce the error due to disturbance. For this we assume that a step disturbance is applied. Then ed of infinity, the steady state error component due to step disturbance is found to be equals -1 divided by limit s approaches to 0 1 over g2 of s plus limit s approaches to 0 0 g1 of s. Now our aim is to reduce the steady state error due to disturbance. This equation shows that steady state error produced by step disturbance can be reduced by increasing the DC gain of g1 of s or decreasing the DC gain of g2 of s. Because if we look at the relation, error is inversely proportional to the denominator, where denominator consists of DC gain of g1 of s and DC gain of 1 over g2 of s. If DC gain of g1 of s increased or DC gain of g2 of s is decreased, will result in a high value of denominator, and 1 divided by high value of denominator will give us a reduced value of steady state error due to step disturbance. Dear students, now we will find out steady state error component ed of infinity for a system given in figure. In this system, it is assumed that a step disturbance is injected to the system. For solution, we will start with the relation from the previous slide, which relates steady state error for step disturbances. In this system, controller part consists of gain whose value is 1000, where plant part is represented by transfer function 1 divided by s into s plus 25. Now applying the limits, we achieve -1 divided by 0 plus 1000 or equal -1 divided by 1000. The result shows that steady state error produced by step disturbance is inversely proportional to the DC gain of g1 of s, and the DC gain of g2 of s is infinity. Dear students, now we will study steady state error for non-unit feedback system. Till now we have studied mostly systems were having a unit feedback, but control system often don't have unity feedback system. The feedback path can have a pure gain other than unity or have some dynamic representation. If you look at the figure A, in this we have a general feedback system showing input transducer G1 of S, controller and plant G2 of S, a feedback path H1 of S. Now here the output of summing junction is not a steady state error, and this will be known as steady state actuating signal. The relation for steady state actuating signal is given here. Dear students, now We can find steady-state error for a non-unit feedback system by two methods, either by making calculations and developing relation for steady-state error, or by converting a non-unit feedback system into a unit feedback system. Now we will make steady-state error analysis for non-unit feedback system by converting it to a unit feedback system. For this, first we will push the input transducer G1 of S, so our forward path transfer function will be G of S equal product of G1 of S and G2 of S. And as per rules of moving the blocks, the feedback path will have equivalent system H of S, and this will be equal to H1 of S divided by G1 of S. Now here in feedback path we have a non-unit feedback system H of S, so the output of summing junction is not the steady-state error, which was difference between input and output, and output of summing junction is actuating signal, which is EA of S. If reference input R of t and output signal C of t have same units, then we can find steady-state error, and that will be equal to R infinity minus C infinity. Dear students, now we will start converting our non-unit feedback system into a unit feedback system. Figure B represents a non-unit feedback system. For converting it to a unit feedback, we will add two branches in feedback path with a gain of +1 and -1. Students, here we are converting our system into a negative feedback system. So the branch with a gain of +1 will be added such that its gain will be -1, and its algebraic sign at the summing junction will be negative. So minus into minus will be positive, and our overall system will be negative feedback system, as shown in the figure C. Dear students, if you look at the figure C in the previous slide, the feedback system H of S and the both branches were in parallel. So we will add two branches, H of S and the branch with negative gain. Then we will combine feedback system, which consists of forward path transfer function G of S and system H of S minus 1. After finding this equivalent system, we will be left with forward path transfer function and a unit negative feedback path. And this will be our equivalent unit feedback system, represented in figure E. And here the difference or output of summing junction will be steady-state error E of S, which will be equal to input minus output. Students, now in the upcoming example, we will find the steady-state error for a non-unit feedback system. Also, we have to find system type and the appropriate error constant associated with the system type. The steady-state error we will find for a unit step input. Also assume that input and output have same units. Students, now we will start the solution. The very first step in finding the steady-state error is to find out the stability of a system, whether the non-unit feedback system is stable or not. For this, you will check the characteristic equation 1 plus G of S into H of S equals 0 with the help of Roth-Hurwitz criteria, and find out location of or planes of the poles. Now after determining that the system is stable, now we will start the solution for steady-state error. After looking at the forward path transfer function g of s, which is 100 divided by s into s plus 10, one may impulsively declare that system is to be type 1. For a unit feedback system with one integrator in forward path or a system of type 1. But here the case is a bit different because we have a non-unit feedback element, and the plant's actuating signal is not the error between input and output. So as first step in solving the problem, we will convert our non-unit feedback system into equivalent unity feedback system with the help of forward path transfer function g of s and feedback path transfer function h of s. The equivalent forward path transfer function will be g of s divided by 1 plus g of s into h of s minus g of s. Dear students, with the help of equivalent forward path transfer function ge of s, we will convert our non-unit feedback system into a unit feedback system. If you analyze the ge of s, we don't have any integrator, so this is a type 0 system. And the appropriate static error constant associated will be a position constant, whose value will be limit s approaches to 0 ge of s, and this will be equal to minus 5/4. Now here the steady state error associated will be 1 divided by 1 plus position constant, and this will give us a value of minus 4. The negative value for steady state error implies that output step is larger than the input step. Now if any of you have any questions, please ask.